Hello everyone. Good evening to everybody.
Hello.
Good evening.
Okay, good. Okay, that I have to explain. Okay. So week 6, right? Let's start that. Linear transformation, ordered basis matrices, image and kernel, and so let's have a brief recap of linear transformations. What were those? Okay. So linear mapping, what we said that you have seen a lot of functions till now. So what are functions? Basically, functions convert some variable into another form. So it could take one variable, two variables. So it can take any input like x and y, and it can transform it in some form. Suppose this function is transforming like this. So this is called transformation. Okay, but it is not linear. Okay, as you can see, the highest power is 2. So that's why it is not linear. It is a quadratic transformation like this. But here, if I take two variables, so I can make any kind of transformation. So what kind of transformation we want? We are only going to look for linear transformations. Okay. So functions in functions we have seen like this x plus 3y we did. Okay. But what was the case in this one? We are not going to convert only a single output. In functions, we mainly consider a single output, but here we consider as a vector. So vector have multiple components. So it means you can consider it as a lot of outputs that you are going to give. Suppose if you want to convert a vector that has two components, x and y, so you can give the output like x plus y, your first component, and second component, x minus y. Okay. So these two components. So this is called the linear transformation. Here we are going to transform each component as a linear combination of the variables that are provided or the components of the vector that are provided. So you want the result component as a linear combination of the provided components. Okay. So here you can see some examples how linear mapping is done. Okay. So let me consider, yeah, linear mapping. You can see here you are given a vector. Okay. From R3 to R3 it is defined, but actually it is from n dimension to n. Okay. So here a linear mapping is done. So where we are taking a vector, or we can say multiple inputs we are taking, and we are transforming it as we want by linear combination of these components. Okay. So after that, we have seen that in linear transformation, one thing is common that, yeah, okay. So one thing is common. If I want to transform, suppose I want to transform any vector v1. So if I have two vectors, so if I transform it to v2 and alpha times of this one and beta times of this one. So if it is a linear transformation, then most of the times we can write down, or almost every time we can write down it like this. Transformation over this plus beta times the transformation over
Sir, you
v.
are discussing week 5 and week 6 both.
Yeah, a little bit of week 5 I am considering so that fastly you can pace up with the week 6 content.
Okay, sir.
Okay, so a brief recap I am giving. Okay. So after that, you can consider here, you have seen a lot of examples how linear transformation works. So every linear transformation has these two basic properties. Okay. So first one is this, that if you have any combination of two vectors, then you can break it down in this way. Okay. And if you are transforming any scalar multiple of the vector, so you can multiply the scalar unit with the transformation of that vector. Okay. So it works only in linear transformations. Based on this, you have seen a lot of examples. Okay, here it is. The next thing was the transformation. Suppose in transformation, we consider one vector space to another vector space. Okay, transforming all the vectors inside this vector space, and we want to transform it to the vectors that are inside this vector space. So basically, one constraint that we take care that the transformation of zero vector of the domain will have an image as zero vector of the range or the codomain space. Codomain. Okay, and here it's the domain. So domain is V vector space and it is W. Okay, range space is something else that we will consider. Okay, we will see that in just some time. So basically, there is a constraint that all every time the zero vector of this vector space V have if we transform that using any linear transformation, so it will mapped with the zero vector of this W vector space. Here you can see the example, because we can write down the zero vector as 0 plus 0. Okay, if we break it, so we will get two transformations like this, and here we can add these two and we will get this on the left hand side, and on right hand side we have two components like this. So we can see here, we can, by using the cancellation law, we can cancel two things, and what we will get the transformation of 0 as 0. Okay, so let's move on. This you have already studied in week 5. Okay, images. What are images? Images you have seen already that what are images. If you want to transform any point, so if you are transforming, suppose 1 comma 0, sorry, here you can take the example. So it's a image. This part is the image of this point. It is in R2 and it is also in R2. It is called the image. Same here, it is the image. So you have transformation, you have a general form of describing the transformation. So if you have some basis and you know the transformation of those bases, so you can calculate a general transformation formula. Like here, that if any point like x comma y is given, so what will be the transformation for that? You can write it by writing the component or writing the x and y component in form of the basis, and you can apply the transformation and you will get the answer. Okay, so you, by this method you can find out the general form of transformation from of a vector to another. Next was cases like injectivity and surjectivity. So in injectivity, you are aware that uh, it states that if you have a vector space here, you have a lot of vectors here, okay, and another vector space here, W and V here. So if you want to uh, match these things, if you want to have a linear mapping, so you want to map these things. So in injectivity, it states that if a transformation is injective, it means no two points can collide with the same image, means no point inside this W can have two pre-images. Okay, these are called pre-images. So no point can have two pre-images. Okay, one thing you can always consider that in linear transformation, this is also not allowed, or any transformation that one point has two images, it is not possible. So don't consider the vice versa case. It is something that you can't have two points having the same image. Okay, or in briefly, if I want to tell, then there exists only one vector, zero vector of the vector space V, which is mapped with the zero vector of W vector space. Okay, if there is more than one vector that is mapping with this, so we can say that it is not injective.
Sir, even
Okay,
one, if a point it has two pre-images, then also it won't be considered, right? In linear transformation.
what?
If a point in W has two pre-images, say for example,
Yeah, two pre-images are there, so we can, yeah, we can say that it is not injective.
it is not injective.
Yeah,
But it can be a linear
you can
transformation, right?
consider, yeah, it can still be linear transformation, but not injective. Injectivity and surjectivity are two separate cases about the two separate properties of linear transformation, you can say. Okay, so why is it? So you can consider, suppose I have two vectors that have same images, TV1 and TV2. Suppose it is also vector W and it is W. So what I can write, I can add these two left hand sides. So what will I get? Transformation of V1 plus V2 will be equal to 2 times W. Okay, and I can also write this thing as transformation of 2 times v1 is equal to twice of transformation of v1, that is nothing but 2w. Okay, so if you compare these two values, so what you will get that v1 is equal to v2. If you compare these two things, that they are equal, so you will get this. It is only possible in an injective case, okay, that if two vectors you are supposing that have same images, so you must say that these two vectors are equal. It is a constraint in injectivity. In surjectivity, what we consider, let me erase this part. In surjectivity, we have a vector space W here, which belongs to R raised to the power n dimension, suppose. So you must have, for all these points inside this vector space, you must have a pre-image in the vector space V. So only then you can say that it is a surjective linear transformation. So here you can see injectivity and surjectivity. Okay, we also say these terminologies as monomorphism and epimorphism. If a vector space is surjective, we can call it as epimorphism, and if a linear transformation is injective, then we can call it monomorphism. And if both are properties are satisfied, then we can say that it is isomorphism. After that, let's go to the null space and range space directly. So in this one, null space and range space, what are those? So range space is basically that space that is covered by doing the linear transformation. So if I give you, suppose, a transformation like this, x comma y will be transformed to, suppose, x comma 0. Okay, it is a point in R2. Okay, it is a vector space of R2, and it is also a vector space of R2 dimension. Okay. So now, what will be the range space of this one? It is stating that x can take any real value. So the range space here, consider all the points in this form a comma 0. So what about the points where the y coordinate is not 0? About suppose 1 comma 2 and 1 comma 3. So there are several points that are lying outside the range space. It is the range space, and the remaining part is inside the codomain but not inside the range space. Okay. What is null space? Null space basically those vectors whose transformation leads to the zero vector inside this. I said that if a relation is, yeah,
So that xy is a codomain and this x0 is a range.
yeah, it is in range.
Okay, sir.
It is a linear transformation that we are applying on this to transform it into this vector.
Yes, so
Okay.
that's xy we are taking as a codomain.
Yeah. XY, no, not this is as domain, and it is as the codomain is actually all the points in the R2
Okay, so that R2 is a codomain.
codomain. It is codomain, and whatever be the image we will get for all these points will be inside the range
Range.
space.
Okay, sir.
And null space basically constitute all those vectors from the domain whose image is zero vector inside the range space. So you can find out all those points. So maybe there are infinitely many points in most of the cases. Suppose here, uh, here is a, you can find out, suppose let me write down t of x comma y is equal to zero vector. So what is zero vector? 0 comma 0. So transformation, what will that be? X comma 0. So it is 0 comma 0. Okay. So all the transformation in which you have x value as 0, all the vectors that in which the x component is 0, so you can say that it belongs to the null space of this, or it belongs to the kernel. Okay, so means 0 comma 1 inside the kernel or null space, 0 comma 2 it is also 0 comma pi, it is also inside the null space. Okay, is that clear?
Sir, can you explain this once again?
Yes, sir.
Okay,
And clear.
null space constitute of those vectors whose range or whose image basically is a zero vector.
Zero. Correct.
You can see here that kernel of a T is all those vectors inside V whose images or whose after transforming them, you will get a zero vector. So here what I did in my case, I took the transformation Tx comma y is equal to x comma 0 I was taking. Okay, the general transformation. So
Okay.
in this case, if I can want to find out all those points whose image is zero or a zero vector, so I compared it with 0 comma 0. So the
Okay.
last component is matching, that's fine, or the first component is having the value 0. So we got one variable's value as 0, but what about y? Y is a free variable or an independent variable. It can take any value.
Okay.
So we have no boundation. So all the points which has x component as 0 and y can take any real number value. So
Sir,
it will
but
be inside.
before we this we said that y component of after general transformation and that we are taking are equal,
Yeah.
and now we are taking as y as a variable, free variable.
Sorry, what are you trying to convey? Can you please elaborate?
Sir, there you said that after general transformation x comma 0 is
Yeah.
equals to 0 comma 0, and the y
Yeah.
component of both the general and the what we have assumed is 0 0, and after
Okay.
that you find that x is equals to 0 and
Okay. Yeah. I'm
y,
saying that second component is matching with this one. This y is not that component. I am talking about this part. It is matching with this. I am talking about this variable that we provided as input.
okay sir,
It is
okay,
after the
okay.
transformation. Okay, yeah. It is after the transformation that we are comparing. So I am talking about this variable that how many vectors, uh, all the vectors are going to be, or some of them are going to be collide with this kernel. So
So,
all the
so,
points here, yeah,
so, sir, you are saying that, in place of if y is a free variable, then it can take any r, right?
yeah, any real number it can take.
Any real number. But sir, in that case, say for example, when we say like for a linear transfer, oh sorry, that is for a onto function. Okay, t of zero is zero. So
Yeah.
in that case, when we say t of v equal to zero, but in this case, v will not be entirely zero, right? In this case,
Sorry.
x comma y, if y is a free variable.
Yeah.
Post transformation, it would be zero, right? The transformation, whatever the y you take, it would
Would be zero.
convert that to zero.
Yeah, it will convert. It will be converted to zero automatically.
Okay
So
sir,
whatever
get
be the
it.
y component.
Got it.
Basically, we are finding the vectors inside this V vector space or the domain. We are not talking about codomain. So inside the range space, we are just checking that how many of these vectors are colliding with the zero vector. Have the image as zero vector. So we got that all the points where x is zero will collide with this one. So we are not constrained over y values. So y is a free now, free
So
variable. So it can
basically, this one will not be a one-one function, right?
This is not an
in
onto.
it's not one one.
It is one
In
one, but not onto.
what?
So this is one one, but not onto, sir.
It is, I think, it is also not
Not one-one, right, sir?
not one one as well
Okay, okay,
because
yes, yes. It won't be one one.
It won't be one-one, right?
Yes,
it won't be on one because I
So
said that if
transformation
zero
of
vector,
anything, if we are taking zero with any other, say for example, 0, comma 1, 0, comma 2, it will give me zero only, right?
yeah,
yes, yes.
So, so, so basically,
what?
zero will have many pre. It can have many pre-images, right?
Yeah, it can have many pre-images because 0 comma 0 has a lot. If there is a null space, it means if the nullity is more
Right.
than one or one, okay, so it clearly states that it is not injective.
Not yes, not in. Okay, okay,
Okay,
okay.
because a lot of vectors are colliding with this zero vector, so that's why it is not. Okay.
Hmm. Infinitely many solutions, basically.
Yeah, yeah, yeah. That's it. Okay. So here we have seen images and range spaces we have considered and the null space we have seen. So you can see here null space of a linear transformation is a vector subspace of V. Okay, yeah, we have already seen this that it is a part of vectors that are inside the V and that are having the image of image as a zero vector of this vector space W. Okay, transformation is vector subspace of V. Okay, image or range space is a vector space of W. Okay, so in image, when I am saying that range space, So I took all the points in this form x comma 0, where x can take any value. So it is a real number, but y is constrained as 0. Okay. So all the points in this form are inside the range space of the above transformation. Same thing is written here.
So,
And in null space, yeah.
so when we say range space, are we talking about the column space?
No, we are talking about this W. When I said the linear transformation we are doing, so from V vector space, we are transforming these vectors into this form of W. Okay. So there are a lot of vectors inside. Okay. Mainly we consider, suppose R2 we are considering. Okay. But not all of them have a pre-image.
Correct.
Some of them remain without pre-image. So only those points which are having pre-images, we consider them as range space.
Okay.
Okay. And inside this V, whatever be the value, suppose there are several vectors and some of them have the image as a 0 vector. Okay. So we consider these vectors as our null space or kernel. Okay. I hope this is clear now.
Yes, sir.
So could you explain once again, please?
Okay. Let me explain it. Sorry. Just a minute. Okay, here it is. Eraser. Okay. So what was I saying, that in transformation we transform the vectors of some vector space into another vector space vectors. Okay. So if I am transforming, so suppose it this vector space contain a lot of vectors. Okay. So some of them vectors are here. Okay. And same here inside W we have a lot of vectors here. Okay. So what is range space basically? Out of these W or out of these all vectors, those vectors which have a pre-image inside this.
Right.
Suppose this is a pre-image of something. Okay. So this is a pre-image. Okay. And this is a pre-image. So we will take only those vectors which have pre-images. It is called the range space.
Okay, okay,
If I
okay.
take only those vectors which have pre-image. Okay. Now
Not the
what
entire.
about kernel?
Yeah, okay.
Yeah.
Okay.
What about kernel? We take only those points from this. Those have image as 0 vector of this. Suppose this is the 0 vector. So I will take only those points which are having image as 0 vector of this. So I will take these points. This is my kernel. Okay. So now let's.
So, sir, there can be many kernels, is it? I mean, so.
Yeah, there are a lot of vectors. In the earlier case, you have seen that all the points in this form, we are getting x comma 0 as range space. So all the points in this form 0 comma y are inside the kernel.
Kernel.
Okay, all the points in this form where y belongs to a real number. Okay, so it can have a lot of. So we just find out the same. It is like that you have solved in your previous cases, the null space when you are considering matrices. So same like that. So you can find out a basis for this, that all the points with 0 comma 1 set span of this set will be inside the kernel. Okay.
So basically the solution space.
Yeah. Solution space for transformation which has image 0. So you can consider that. Okay. So this is done. So what is nullity? Nullity is basically the dimension of the null space. And same here, the dimension of image space or range space is called as rank. Okay. So now let's move. T is an injective linear transformation if and only if kernel of T is equal to 0. Okay. So you can see that we can only say that T is injective, means all the points inside the range space have only unique pre-image. Unique pre-image. Okay. Yeah, that's fine. Okay. Unique pre-image it is having. It can't have multiple pre-images. So in this case, you can see that how can we prove that kernel of T is equal to only this 0 vector it is going to consider. So assume that transformation of V is equal to 0. So T0 will also apply here, that T transformation of 0 always mapped with the 0 vector here. Okay. Next thing what we can apply, that every point if I want to find out here, TV, I want to find out. So if it is equal to the zero vector, so every point or the image of this vector v is unique. So this v is unique, as I said that it can have a unique pre-image. So means this v is unique. And what was that? We are aware that zero vector of this vector space mapped with this one. So this can only take this value. It can't take any other else if it is injected. Okay. Next is range space when subjectivity we are talking about. So it is stating that any transformation is surjective only if and only if the image of that transformation is equal to w. That is the same thing that we have already figured out, that if all the points inside this w have some pre-image, then we can say that it is surjective. So it is same thing. It is saying that if we find all the images of all the vectors, if we find out all the images of all these vectors, so if all the point inside W are covered, then we can say it is surjective. This is same thing, nothing else. Okay. Let's move on. Okay. Okay, it is saying that any n-dimensional vector space is isomorphic to Rn. Okay. Means if you take any n-dimensional vector here or n-component vector that is having my first vector component as v1, v2 like this and v8 or vn suppose. Okay, so if you want to transform, so you are going to use any linear combination of these vectors. Okay, so you are going to take any linear combination of these vectors. So any n-dimensional vector space is isomorphic to Rn. Okay, so Rn if you are going to do, so if you are applying any transformation in this, so there are n independent or n free variables you are having here, and inside the range space or inside the codomain you are also having the vectors that have the same n components. So you can define n independent components. Okay, so you can make it isomorphic to in. Means each point can have an image. You can just verify this thing by simply writing an transformation v1, v2, v3 up to vn to a vector v1, v2, v3 and up to vn. Same transformation we are applying.
So basically, this is both injective as well as surjective, right?
Yeah, it is both. Because all the points are linked and have unique images there. Okay.
As
And
well as
all the
free
points
is
of
there.
this Rn are inside the range space here. Okay, let's move. Matrix representation if we want to do. So how do we do this thing? We consider a basis firstly. Okay, I want to represent any transformation as matrix. So how can I represent this? I require a basis for my first domain vector space. Okay, domain and codomain. Okay, so they are considering the standard basis here in this example. So if you apply the transformation on the first vector, so it will be transformed this. You can write it as a basis by using the basis of the codomain space. So you write this vector as like this as a linear combination of the basis. Okay, same you can apply on the second vector and so on. If it is of Rn, so you can write all the n vectors in this form. So after applying, what you have to do, you have to write, I think, all the columns as row and rows as column, I think. Let me check this. Yeah, here it is. The 2 0 is there. So you will write this as column, first column, and 1 1. So you write it as second column. So this is the matrix representation. Okay. Okay, that's fine. You are given a linear transformation like this, and you are given a basis of vector space V. Okay, and gamma is the basis of W, vector space W. Okay, so you are saying that if transformation of Vi can be uniquely written as a combination of this. Yeah, that's fine. It is same thing. I think this is transformation of matrix they are explaining here.
Sir, I'm really sorry to interrupt. So in the
Yeah,
above one where you show the matrix transformation, so basically it's
yeah.
the equations are written in they are written in row form, right? 2, 1, and 0, 1, if I'm not wrong.
We write the equation, we write the transformation of V1 here, okay, and we use the linear combination of the basis of W. And so whatever be the coefficient that we are having, so we write down it as columns. In first equation, uh, we are writing A11, A21, AM1 as first column. So we are converting the rows as columns and columns as rows.
So in the above one, how is it written? Can you just go up if you don't mind? Two zero
In
zero
this
one.
one, in this
Yeah.
one, we also did the same thing. 2011. In above one, what I was thinking, because here you can see that 20 and 01 it was. So that's why I took the next example. Because in this case, it was not clear that whether it was written as rows and rows are changed with columns or not. Okay.
In the above one, it's not clear, right, sir? Okay, okay. This one is clear.
Yeah,
200.
because we can't conclude. Yeah, it is okay. I know that it was written in this way that we are writing the rows as column, but when I looked at, so it wasn't clear that time. Okay.
Okay, okay.
We write every time like this. Okay, so here is a transformation given. So what are we doing here? So t x y z, okay, like this. So firstly we took any basis, standard basis. It is saying that we have to find out for standard basis. So transformed, what are the standard basis? 100, 010, and 001. So we find out the transformation using this general formula. So whatever we get, we write it as a linear combination of the basis for this vector space. So we wrote like this: 120, 120 here, 033, 033, and minus 1, 1, 3. So this is the matrix representation. Okay. Same here, nothing else. Same here. Okay, anything's remaining. Okay. Finding basis and that thing. Okay, let me cover this part as well. Yeah. So let's do some questions based on this. So this transformation I already took as example. So let's do this question. The transformation of xy as x comma 0. So here you can see it is saying that the matrix corresponding to T with respect to the standard ordered basis is 10. Okay, we are considering for both codomain and domain is this. So if I look at, so what was my transformation? My transformation was like x comma y is equal to x comma zeros. Okay. So if I take 1 comma 0 here and I transform it, so it will be transformed to 1 comma 0. That's fine.
Yes.
So what I can write this transformation of 1 comma 0 as 1 times 1
One.
comma 0 plus 0 times 0 comma 1, right? Next
Yes.
transformation I want to apply on 0 comma 1. So what I can say is 0, 1 comma 0 and plus 1 times 0 comma 1. Okay, so it is saying that okay, 1 comma 0 for both comma domain and domain, the matrix. Okay, okay, it will be transformed to 0 comma 0 when we are applying the transformation on t 0 comma 1. So it will be mapped with 0 comma 0, right?
Yes, sir.
So
But
that's
it
why
is
both
given zero
components
one.
are 0. That's why the, yeah, that's why the option 2 is correct. Okay, it is stating now in the option 3, you can see it is stating that it is neither 1 1 nor on 2. Okay, we have already figured out that it has a null, it has a kernel space. Okay, that has vectors other than the 0 vector. Okay, there are several vectors more than sorry, other than the 0 vector. So it has a some nullity, and if it is having some nullity, so it is not injective. Same not onto means all the points inside R2 don't have the pre-image. So that's why it is correct, and it is saying that T is 1 1. No, it is not 1 1. We have already seen this. Now next question, let's see. There is a vector space
Sir,
W that
sir,
is
sir.
given all the points. Yeah.
Sir, in the last question, you made some inference, sir. Can you just repeat that, sir? When you said that in kernel space. regarding the
Okay,
kernel
okay.
space. Yes.
Basically, in kernel, if you have only a zero vector,
Yes.
kernel space or null space, you are having only a zero vector. So its nullity is zero,
Correct.
right? If you have any other vectors or any other dimension, so its nullity is going to be more than zero.
Yes.
Okay, if its nullity is more than zero, then you can say that it is not 1, 1.
Okay.
Because nullity means greater than zero means more than one vector is going to have a image as zero vector. Okay, so there are more pre-images of a point. Okay, more than one pre-image is available there, so we can say that it is going to belong to the kernel space. So that's the thing that I said. Okay, so now let's consider another vector space here that is given as w, x comma y comma z, all those points that can be written in this form. Okay, so we are given a basis here for w. Okay, and we are given a transformation is a linear transformation such that we are transforming first, okay, like this and this. So now we have to find out the general form of this. What is the general way of a transformation? So how can we find it out? So first of all, I said that we will write down x comma y comma z. We want to find out this transformation. So how can I get this? Okay, so suppose I want to multiply a times 2 1 0. Okay, so I can simply replace this firstly, that I am only going to take these type of points. So I can remove this and I can write 2y plus z comma y comma z, all these type of points. So what I can say, I will multiply a times this plus b times 101 to get 2y plus z comma y comma z. Okay, so I have to find out that what linear combination of these two vectors will result me in this vector. Okay, this general vector I will get. So let's write down this. So what are my three equations that I will get? 2a plus b is equal to 2y plus z. Okay, a plus 0 will be equal to y and b is equal to z. So from here a value is y and b value is z. Okay, so if I put it here, so I will get this equation also correct. So I got the solution that a is value y and b is value is z. So I can write down that the transformation of this one will be same as the transformation of uh, y times 2 comma 1 comma 0 plus z times the transformation of 1 0 0 1,
101.
like. Okay, so if I apply the transformation now, so it is same as y times transformation of 2 comma 1 comma 0, right, plus z times the transformation of 1 comma 0 comma 1. So these two transformations are given already here, 1 comma 0 and 0 comma 1. So I can write that y 1 comma 0 plus z times 0 comma 1. So if I multiply now this, so I will get y comma z. So option 3 is correct, right?
Yes, sir.
Okay. So that's okay. Now next thing is given here in form of x, it is also applying. So from this value of x, what is the value of x? X is 2y plus z. So I can write this y, 1y, okay, 1 is there, okay. So what I can say, I can get the value of z from here. Okay, let me write down the z value from here. So z value is nothing but x minus 2y, right? From
Yes,
this
sir.
equation.
Yes.
Okay. So I can put the z value here. Okay, x minus 2y. So I will get this. Okay.
Correct.
And what I can do, you are aware that what is this? X minus y minus z. In place of x, I can write this x minus x is equal to 2y plus z minus y minus z. So if you compare this thing, this is nothing but y. Okay, this is nothing but y. It is y.
Sir,
So this
just
option is also correct. Yeah.
so just wanted to ask you, like, in case these problems come, like how, what is the way to this is the only way to approach, right?
Yeah, this is the only way.
Okay.
So in this one, what you do, you write down the general form. So the general form is like this. Okay, if
Okay.
no relation is given, but relation is given, so we eliminated one variable
Correct.
and used only two variables. Okay, and then what we did, we find out a linear combination of two vectors
Okay.
such that we can get the general form. So I wrote it like this with the help of these two bases. I
Okay.
got it and I
Okay.
transformed it. So I got my transformation as y comma z. Okay.
Okay.
But if you observe carefully, the option 3 is okay, that is correct. But why is option 4 is also correct? Because it is using the variable x and we removed it. On my first attempt, I
Yeah.
removed it. Okay.
We basically
So we
check
can also,
like x minus y minus z
what?
is equal to y or not, right?
Yeah,
In option 4, we
that
basically
is,
check if f x minus y minus z is equal to y or not, right?
yeah. That's fine.
Okay.
So it is nothing but if you just do the simple transformation here on this option, so you will get the exact same answer.
Okay.
If you nothing, if you instead of doing this calculation from the back side, you can directly change this option as well. What is x minus y minus z? It is y. And what is x minus 2y? So from this equation, you can get it is z. Nothing. That's why this option is correct and this is correct. Other two are wrong, okay? So now let's move. It is saying that t is 1, 1 on 2 or something like this, okay? So in this one, if you have seen that we transformed x comma y comma z to y comma z. Okay, x is nothing. X is some linear combination of these two. So it has a dimension 2 here. Two free variables are there. X value can be derived with the help of these two variables. So it has dimension 2 here. Dimension of v is 2, right? And here if you observe these two values, so these two are independent variables. So its dimension is also 2. Okay. So we said that if we have dimension equal both sides, so what we can say that it is isomorphic. If range space dimension matches with the codomain space, sorry, domain space dimension.
So because of this variable x, because of this equation x equal to 2y plus z, it's two dimension, right?
Yeah, two dimension because two free variables are there.
Okay.
If one of the variable is something like y comma y, it is so it has one dimension only
One dimension.
because one variable can define the other part. If I have the value of first part, then I can define the second is going to be same.
Sir, what if we
So that's
need
why
to find 1 1? How to check 1 1 and onto here?
1 1 and onto you want to check. Okay. Okay. In this one, okay. So 1 1 and onto you can simply check by that formula as well if you want to transform.
Zero, zero,
Suppose
zero.
uh, all x comma y comma z for 0 comma 0 comma 0. You can also apply this thing.
Right.
So to zero vector, what is going to be at the zero vector? So suppose I find out the solution for this. So what is this? This is nothing but the transformation of this is y comma z. Okay, directly y comma z is equal to 0 comma 0. Okay, this is 0 comma 0 only. Okay. So if I compare y value is 0, z value is 0, and from y and z we can derive the value of x. So x is also 0. It is only possible when all three variables are 0. Okay, so it don't have any infinitely many solution. It has only one unique solution, that is this. So that's why it is 1 1.
Yes, sir.
Okay.
Okay, and on two case you can consider, you can simply just observe this thing. You don't have to do calculation that it is of dimension 2 as well as it is of dimension 2. So no dimension is lost. So we can say that
It is onto.
It is on two.
it is on 2, yeah, because it is of two dimension. Okay, so all the points can be covered and independently they are. So that's fine.
Okay, sir.
Okay, so okay. So next is this. What will be the matrix representation of T with respect to the basis beta for W and gamma for this R2? Okay. So what is this beta? Where is this? Okay, this is 210 and 101. Okay. So transformation of 2, 1, 0 and transformation of 1, 0, 1, right? Something else it was. Yeah, it is 1 comma 0 and 0 comma 1. Okay, that's fine. It is 1 comma 0 and it is 0 comma 1. So how can I write these two as a linear combination of these two? So basically what I can do, I can say 1 by 2 times of first 1 comma 1 plus 1 by 2 times of 1 comma minus 1, I think, right? If I do this, so 1 plus 1, 2 divided by 2, it will be 1 and 1 minus 1, yeah, that. In next one, what I can write, how can I get this? So I can write 1 by 2 times 1 comma 1 minus 1 by 2 times 1 comma minus 1. So now if I represent it as matrix, so I can get 1 by 2, 1 by 2, and here 1 by 2 minus 1 by 2. So I can take 1 by 2 out of the matrix. So I can write 1 by 2 outside and 1, 1, 1 minus 1 like this. So where is this? It is the option. Is that clear? Is that clear? Anyone facing an issue?
So up till this one, it's clear, but then like when you, how did you reach to the matrix? Can you explain once again? Yeah.
Okay. How did I write this coefficient, right?
This is fine, sir. This coefficient is fine. The moment,
Fine.
like, this matrix, final matrix, this thing. Okay, half, half.
We
Okay.
have just
How
written
did
the
Coordinates,
coefficient
coordinates.
vector only.
Okay.
So,
Okay, these are the coordinates, right? Half and half and half and minus half.
yes, sir.
Yeah,
Coordinates.
these are the coefficients of these things. So I just did. I wrote the row as column here, 1 by 2, 1 by 2, and 1 by 2 minus 1 by 2, I wrote here, second column.
So these
This is
coefficients
my
are the
matrix.
coordinates, right?
What?
These coefficients are basically the coordinates only, right?
Yeah. These are going to be the entities inside this matrix. Yeah.
Okay.
Okay. So what I did, I multiplied it by 2 inside. Okay. I multiplied it by 1 by 2 times 2. So I multiplied it 2. So all 2's got cancelled. And remaining is my matrix 1 by 2 times this. So now let's move. Okay. It is asking, okay, we are given a relation, a transformation here like this. Transformation of x comma y is x comma 0. So it is again asking that what is going to be the spanning set for these two things. So as I said already that the range space consists all the points in this form x comma 0 where x belongs to real number. So I can write it as x times 1 comma 0, right? So it is a linear combination of this vector 1 comma 0. So it is going to be span of the set that is having this vector only 1 comma 0. It is my range space. Okay, now it comes to null space. So I said that y is a free variable. Y can take any value, but x value is fixed. So all the points in this form 0 comma y will be inside my kernel. So I took out this y. So what will I get? 0 comma 1. So it is a linear combination of 0 comma 1. So my kernel will have a kernel of t is nothing but kernel is span of the set that is having only this element 0 comma 1. So you can see here it is and here it is. Is that clear?
Yes, sir.
So
Finding basis for null space. Yeah, what?
could you explain that one again? The previous one.
Okay. In this one, so what is range space? Range space basically all those points which we are going to get by transforming
Right.
by transforming the domain space. Okay.
Domain.
So we are
Sir, range
transforming this.
space
So we are
is same
getting
as image, no?
what?
Range space is same as image of transformation.
Yeah. Range and image both are same thing. Okay. If you are talking about range and image, it is same thing.
Okay, sir.
Okay. So I said that we are transforming vectors of R2. Okay. And we are transforming in its transformation, we are only getting the vectors of this type, where my first component is X. And
So,
what is X in this vector space? It can belong to any real number.
correct.
So all those points in this form. So I can find a basis for this point. So I can remove this variable outside, or I can move this variable outside, and what will I have left here? 1 comma 0. So I
Correct.
can say that it is a linear combination of this vector.
Okay.
All those point, if it is my subspace, it is my okay. So
Right.
uh, it can be spanned by a set that is having only this vector. This vector is enough to span all these vectors inside this. We can
Correct.
make or derive. Same in case of kernel. So kernel, I said that we want to find out all those points whose image is 0 vector. Okay, so I want to find out all x comma y's for which their transformation, if I transform, so x comma 0 is equal to 0, comma 0. Okay, so I found that x is 0, x value is fixed. So I can fix this x value as 0. So y is remaining still. So
Right.
y can still take any real number. So what is going to be the, so I have to remove this y. So I wrote it outside and 0 comma 1 will left here. So the set that is having this part, this vector, will be my kernel, will be my spanning set for kernel. Okay.
Okay.
So here is a finding basis for null space, range spaces like this. So if we want to find out, so how can we find out? So here is some steps are given. So let's check them. It is saying that you are given a transformation like this from V vector space to W vector space is linear and follow the following steps to find the null space or range space. So find the matrix A corresponding to T with respect to some standard ordered basis. So we will take some standard basis like this. Beta is given for V and gamma is given for W. So these two are bases given here. Use row reduction method on A to obtain a matrix R that is in reduced row echelon form, RREF form, RREF, reduced row echelon form. Okay, then we have to find out a basis for this solution. Same thing that we are going, that we have done in till now. By matrix, what we do, we write down ax equals 0. Okay, for homogeneous case we reduce it to our row echelon form. Okay, and then we find out that how many linearly independent variables are there or free variables are there, and then we write down all dependent variables in form of this. So here something like this, up to this step, row reduction, we have done the same steps. Okay, we wrote it in the row echelon form. So we want to find out the basis for the solution space Rx equals 0 is the basis of null space for the matrix A, and can be obtained by finding pivot and non-pivot columns. Same thing, the dependent and independent variables. Okay, as seen earlier, you can see here.
Sir,
We are also seeing.
am I audible, sir?
Yeah, you are audible.
Sir, how did you find that A matrix? I'm a bit confused.
Okay, the A matrix I find out the same way that I will do the transformation on my, suppose I took my first vector of the basis V1 and I transformed it. So I will get some
W1.
combination of these. Yes, suppose alpha times W1 plus alpha 2 times W2 and so on. So I
Hmm.
write down the matrix as alpha 1, alpha 2, alpha 3 as first column, and transformation of V2, whatever I get, I will write here and write here. So this is my A. The
Okay.
transformation matrix that we form for the transformations above.
Okay. Okay.
Same thing
Basically,
it
it
means.
will be given to us.
No, we are given the transformation, okay,
We are
and
given
then
the
we have to use
transformation
this,
function, and
yeah,
using that
general
we
form
are
of it. Yeah. We are,
getting the matrix.
yeah, we can use the standard order basis, and then we can get the matrix.
So at
Okay.
least the function or the transform matrix has to be
Yeah,
given.
something is given. Yeah, either the matrix is given or you are given the general formula for that. Means how to transform that general transformation is given. Okay. So you will find out all the vectors forms a basis of null space. Okay. Precisely when the, okay, they belong to kernel space. Okay, this is fine. Forms a basis for, use the basis obtained in step 3. Okay. Just to get a basis for kernel. Okay, we can get the for kernel as well, and for range space it is not. By pivot elements, yeah, we will get the range space. Okay. Uh, let's see. Let's see an example directly so that it will be easier for you. Okay. Here you are given a transformation like this. Okay. So what we did, we took the standard basis. Firstly, transformation of 1 comma 0 comma 0 comma. Okay. So what will be its transformation? 2 times x1. So 2 it is, x1 1 it is, and 5 x1 1 it is, and something I'm missing. No, yeah, that's fine. So what it is? 2 1 1. So if I write it down, so how can I write it? Twice of 1 comma 0 plus 1 times 1 0 comma 1 comma 0 plus 1 times 0 comma 0 comma 1. So 2 1 1 I got. So I wrote it here, 2 1 1. Same if I apply on 0 comma 1 comma 0 comma 0. So what will I get? 4 3 and 2. Oh, sorry, 1.
One,
4 3
one.
1. So 4 3 1 I wrote here like this. Okay, we did for all these four vectors inside my basis. I did. So then we reduced it to the reduced echelon form, row reduced echelon form. Okay, RRE form. Okay. So what will be the required null space? We will find out same as we will write it as Rx equals 0. Okay. So we found that there are two independent variables or free variables, that is x3 and x4, because they are not having the pivot elements. Okay. So we wrote x1 and x2 as a linear combination of these two. Okay. Then we put some some standard values to them by firstly giving only one variable value 1 and other all are get 0, other are going to get 0, and all independent variables are going to 0. And in the next case we gave the second independent variable as value 1 and other independent variable will get value 0. Okay, then we got the value of x1 by using this formula, and same here by using this equation we got x2 value. So we wrote here. So this is basically a null space, or it is a basis for the null space. Okay. And if you want to find out that what is going to the range space, so you can see this is my first column has the pivot element and second column has the pivot element. So I can simply move a little bit up. So what is my first vector? 2 1 1 and 4 3 1. So they will form the uh, uh, basis for my range space.
So can you just go
Is
below
that-
once? Yeah. So can
Yeah.
you, okay, this one I got it, sir, x1 equal to minus 9x3. But then they wrote, now, hence the null space is spanned by the vectors minus 9, 3, 1, 0 and 2 minus 1, 0 on where.
Okay, I'm explaining it. Okay, I will explain. If I multiply these two matrices, so what will I get? X1 plus
X1 plus 9x3
get 9 times x3, okay,
plus
plus
2x4
2
equal to
times
0.
x4 equals 0.
Right.
Next equation I will get as
x2
x2
minus
2 minus
3x3
3x3
plus
plus x4
x4.
x4.
equal to 0.
So these two are my dependent variables. So firstly, I will write this x2 in form of this. So what I can say that x2 is nothing but 3x3 minus
9x3
3x3 plus
4,
x4 minus
and
x4.
x1 will be, yeah, it will be
9x3.
minus 9
Minus 2x4.
minus 2x. So now I
Yes.
said that now we have two free variables 3 and 4. So what I will do, I will give x3 value 1 and x4 value 0 in my first case. So if I give here, so I got the x2 value as 3 and x1 value as minus 9. Okay, so what are
Okay.
the values? Minus 9, 3, 1,
Minus 9,
0.
3, 1, 0. Okay.
Okay. Next case I am doing, because I have two free variables, so I have to use the same, just it will be the same as the standard basis that we use. So the vectors that we use, same as here we will use. So now I will give value 0 here,
So 1,
and
0
this
and
will
0, 1.
be 0. Okay, yeah. So now if I use this value 0 here, so I will get minus 1 here, okay, x2 value. And if I use 1 here as x4, so I will get minus 2 here.
So, sir, basically, we'll have to do this by standard basis. This is compulsory, right?
No, yeah, this is compulsory. Means if you want to, because we would just only want to find only one basis. Okay, because we know that it is a vector space or subspace it is, so it can have multiple bases. So this is the good way of finding it. You can use other bases as well. That's also fine. But
So,
this is the
okay,
standard way.
Okay, we can use 1, 1 and 1 minus 1 also. That is also
You
possible,
can
right?
also give, yeah, you can give any kind of values, but make sure that you don't give dependent values. Means you are giving
Independent.
1 1 0. Next time you give 2 0. So you don't give don't like this values.
It will not.
Okay, so
Sir,
this will
and
not.
it is in ordered way only. Like that, first we have
Yeah, it
taken
is.
1 0, then 0 1.
Yeah.
Sir,
What?
no, sir.
Sir, you have said it is in ordered way only, no?
It is ordered means we have to find out only a set. So doesn't matter whether firstly you are giving this one or this one. Okay, because we are going to get a set in set. Don't the order doesn't make sense. We can write this vector
So,
first or this vector.
there can be many null, different null spaces.
Yes.
The answer will be not unique.
Sorry, the basis that we are finding, the basis is not going to be unique because there are a lot of bases for the same null
There
space.
Yes,
Yes.
sir.
Okay, and have many spaces. Okay, but we use consider the standard one. So in which we give the value 1 0 0 0. Okay, then we give 0 1 0 0 0. Then we give 0 1, so on like this. We use
Sir,
the
in a
standard.
standard one also, here we can get two answers if we interchange the value. Like first we have take 0 1, then we will take 1 0, then the value will be somewhat
No, no,
changed.
it is not going to. The answer will be same. Suppose if I give 0 comma 1, so I will get -1 and 2 again. This
Okay,
vector
sir.
I will
Okay.
get
Got it.
first, this
Yes,
I
sir.
will get second.
Yes.
Okay,
Yes,
that's
yes, yes.
only that. Okay, nothing else. It is not a lot, a huge difference.
Yes, sir. Right.
Okay,
So
is that
which
clear?
so which
Just can you explain how to choose x3 equal to 1 x4? It's a random or it's just
Randomly what you can do, you can take the variables. How many free variables are there? Two free variables are there, x3 was and x4 was. So what you can do, firstly give this value 1 1 to this value and all other variable will get 0. Okay, in next time what you have to do, you have to give this 0 and the second variable will get the value 1 and all other will get 0.
okay? Suppose
If
here
suppose
x5 is there,
5 is
then
there,
we
yeah, so this will get 1 and these two will get 0 and all remaining will get 0 as well.
okay, one time
We
only
give
will
the
be what?
value. Yeah. Only one variable, one independent variable will get the value 1, other will get 0.
Okay, sir. Thank you, sir.
Okay.
Yeah.
so just wanted to ask, like, sir, can you share this book also with us if you don't mind?
Yeah, I will share it. Okay. After this session, in TA notes, you will find out this. Okay. I will share this part.
So,
Okay.
this book, it consists all the whole syllabus of maths too, right?
It may be some of the components inside this is more than your syllabus, I think. Some of the components be removed, I think.
Okay. And
So,
this is the suggested book, right? I believe in
yeah,
this
this
also.
was the earlier time it was available in course content, but now it is not. I think they made certain changes to the syllabus, so that's why it is removed, I think.
So it's available on the website, IITM
It is
website.
available.
Which
Yes, sir.
website,
You can
Ravi?
IITM website, the
Okay.
original website
otherwise
from
you
where you
provide it.
might have taken the admission. That site.
And there are
Otherwise, if you
two.
don't find out, then I will provide it in the TA.
So yeah,
Teach
if
you
you
can,
can provide it in the, yeah.
or if you can send the link, then you can send.
Ravi,
Who's
can you
having the
send the link?
Yeah,
The
sure.
link.
Actually, I had raised this question in discourse. They provided the link. I'll share that.
Yeah, please. It would be great.
Okay.
Sure, sure.
So, rank nullity theorem is remaining. So,
Sir, I had a
I
doubt in that previous lab page, sir.
okay in this one.
Yeah. In the range one, sir. Can you just scroll down?
Yeah,
Yeah. Yes, sir. No, sir, the basis of range is given as 211 and 431.
and yeah,
Correct, sir. So, my
yeah,
question is, when you say range space, you said that all the vectors that have an image will be
yeah.
part
That
of
have an
that
image.
range space.
Yeah, means those vectors that have pre-image. We will consider. Suppose my
Range itself
constraint
is an image.
from B to W, so I will consider all the vectors inside this W that have some pre-image there. Okay, some may be not having because it is not possible that it is onto. In onto, all the points have the pre-image. Okay, but if it is not onto, so maybe some of the vectors are without pre-image.
Uh, oh, so when we see this matrix, sir, then
Yeah.
when we see the pivot, the column which have pivot,
Yeah.
I'm not getting how we are concluding that they belong to the range space and remaining are the not part of that range space. That's why, because remaining two columns are linear combination of first two. So
Yeah,
basically, they will also be in that range space, no?
yeah, they are also, but this is the basis. Okay, this is a basis. So
Yeah,
whatever we were going
yes,
to
sir.
form
As
these,
far as the basis goes, I fully agree with you. 211 and 431, but even the remaining would be part of that range space. That's what my question was. If I'm not talking about the basis,
okay, basis means suppose you want to transform, you have some four-dimensional vectors here are, okay. So you are transforming it to a, uh, you are transforming it, let me see a little bit above, just a minute, to three-dimensional space, I think we are transforming it. Yeah, to three-dimensional space, okay. So what was the problem that just like the transformation, let me take it easier one, x comma y that I did is equal to x comma 0. Okay. So in this one, so one of the dimension of this is lost. Okay, one dimension will lose. So this one dimension went for the nullity. Okay, not here. It is not here nullity. You can consider it as range space. Okay, directly don't get it there. Okay. So what I'm saying that now whatever be the points that I am having here, so all there are points, several points are there in my vector space. This one. Okay, some of them collided. Okay, some collided. So some of them points are remaining without any pre-image. So those which are colliding or we are getting. So some of the parts, suppose I got a basis for this part because in two-dimensional space, okay, so I can have a graph like this. So I can have a vector if I am having two independent vectors, okay, so I can span this whole space. But suppose my solution space lies as only one line, so I require only one column, so that is linearly independent column that I had. Okay, other dependent columns I can derive these parts from these two values. Okay, so I don't need these two columns because I am able to derive these things. But these two dimensions are lost, so that's why we have a null space here. Because in place of this, I require four independent vectors I need. Okay, but two were lost to form the null space, and two I am having to form my range space.
so even though we didn't have, the null space would have been only one vector. Still, we would have that, no? Currently, we are having two vectors in null space, but even if we
Yeah,
had that one vector only,
yeah.
then uh,
No,
would
no,
it
no. It is
matter
going
in
to
that case?
span
Yes, in the
because we
span
have
of.
four free. No, no, no. We have four variables here. Okay. So our
Mhm.
vector that we have has four independent directions.
Correct.
Okay. So two directions were lost. Two
Right.
values, the x3 and x4, okay, were lost. They can take
Correct.
any freely value. So that's why they are not having any impact on the range space. So they were lost. So whatever the remaining part will gonna form our uh, range space, and these two will conclude to the null space.
Right,
So that's the
sir.
case only. Okay, if
Oh,
still any confusion, then you can.
sir, I'm still confused. Maybe I'll put the question in the discourse, sir.
Okay, okay. If you face any problem, then you can put there. Okay. I know it is a little bit confusing. You will get it, sure.
Sir, one very basic
So up to you.
uh,
Sir, in this
Yeah.
case, like say for example, because we have two, we have, I'm just saying, because we have, two free variables here basically. So that's why, we are going for 1 0 and 0 1, right? So this is one of
Yeah.
the reasons, right? In case, what would have been the case if there would have been, one free variable only? Then we can take any value, right? for that.
We can take no, we can't take any value. We have to give one value to that free variable. You
Say
are
for,
saying that when we are finding standard basis like this, so we will provide the free variable as value 1.
okay, so basically there will be only one. Okay, okay,
There will be, suppose you have only one free variable. Suppose three variables are there, x1, x2, and x3, and these two are dependent variables, and it
dependent.
is independent. Okay, so you
Correct.
can give value 1 to this, so to find out the basis for this. Okay, this is a standard way. Okay, otherwise you can give any value, that's fine. Okay, but most commonly we use for standard cases 1 is okay.
Okay.
Okay, 1 is okay.
Okay.
Suppose if I give here, in place of this, let's take this example. In place of 1, if I give 2 value there. Okay, so what will be my answer? X2, I will have as -2. Okay, and here it will be x1 will be my -4. Okay, and x3 will be 0, and x4 is -2. So if I write it down, so what is this? -2, -4, 0,
One. Okay, minus.
1. So it is nothing, it is just a twice of this. Or something wrong I did. X2 is x4. X1 is -4. Sorry, x1 is -4. It is -2. Okay, it is -4, -2, 0, and 2. So it is just twice of this. Okay, so if you use any different value here, so it is going to be just a multiple of the standard way. Okay, so don't worry, use standard methods that are okay. Here you can remove 2, you can divide this this vector by 2, so you will get this. Okay. This. So up to this part, any confusion now? Any query?
Sir, not related to theory, just one very basic doubt. Sometime prove the equation or any property. We choose the vector like 0, 1, 1, 0. Here,
Yeah.
I have confusion how to choose that.
Okay, just a minute. Okay, I need to put my charger on this laptop. Just
Yeah.
I've pasted the link of the book.
Yeah, yeah,
Can
yeah, yeah,
can
found it.
anyone confirm whether it's accessible?
Yeah, yeah, it's accessible. I downloaded it. Thanks.
Okay.
Kernel T and null space part is not covered in instructor session.
Yeah,
kernel
actually,
and it is not now. Okay, so I will stop here. Okay.
sir,
No,
just
sir,
wanted
you
to
can continue, sir. We have understood whatever you said.
so just wanted to ask
Okay.
you a very silly question. It's not from this topic.
Yeah.
It's from matrices
Yeah.
actually. Sir, so actually,
Yeah.
like when I was going through the internet, I found in a lot of content that, as far as I know, sir, the zero matrix is not a scalar matrix, right? But in
No,
some,
it is scalar.
sorry,
It is scalar. Zero matrix is scalar.
zero matrix is a scalar matrix.
Yeah,
Okay.
because what is the theory of scalar matrix? You are, if you are aware that all the matrices in this order n cross n are square. Okay, then
Right.
there comes a subpart. All the matrix, all the square matrix, which have the elements other than the diagonal elements as zero. The theory is this, that other than the
Right.
diagonal elements are zero. We are
Right.
not telling about what is diagonal. Okay, we are saying other than the main diagonal element are zero, then it is diagonal matrix. The diagonal element can also be zero.
Okay. So in case the diagonal elements are same, then it's a are like other than zero. Say for example, it's 4, 4, 4, 4, 4. Then it's basically a a non-zero scalar matrix,
Yeah.
right?
Yeah, it
And
is a non-zero scalar matrix. Okay,
but the
non-zero means it is not equal to zero matrix.
non-zero. Okay. Okay. Yeah. Correct. So
Okay.
basically, a zero matrix can be a scalar matrix.
Yeah,
It's
zero
a
matrix is
scalar.
a scalar matrix. Of course it is.
Okay. 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 Fine.
But
Fine.
if it is written in the question that non-zero scalar matrix, so it means it is not going to be zero matrix. It can be like, yeah.
Actually,
And if written non, yeah,
there were two options. In one, it was written as a scalar matrix, and in another option, it was written as a non-zero scalar matrix. So that's why I was having
yeah,
a bit of confusion. So now it's clear to
this
me
was
because zero matrix
okay.
is a scalar
There was
matrix.
Yeah, yeah, yeah. One more thing I want to mention here, that non-zero diagonal matrix, if somewhere it is written non-zero diagonal matrix, then
Okay.
don't make any problem here. That non-zero means diagonal matrix 1 0 0 0 0 0 0 0 0. This is a diagonal matrix and non-zero it is.
Right. So basically, at least one element has
Okay.
to be non-zero, right?
Yeah, one, at least one. Okay, maybe all elements are non-zero, maybe some of them are non-zero, but at least
Mhm.
one is there. Okay,
Okay.
non-zero means it is not equal to the zero matrix. It should not be equal to the zero matrix that we are seeing.
Okay. So
That's the
basically, in
part.
broad sense, zero matrix is a it's a scalar matrix.
Yeah, yeah, it is.
Okay. Okay. Thank you.
Okay. Any other doubt? Anyone having? So it is up to this part. I think it is okay for today.
Yes, sir.
No,
Let's
sir.
see
You
some
can
questions.
continue.
What?
I
You
have
can
asked.
cover, sir, week 6 till week 6.
Okay, week six, others will cover the remaining part. Okay, on the next session, because now you have your quiz one, so you can prepare for that. From week one to week four, you have to cover.
Okay, sir.
Sir,
So
one thing you have
don't be too
said.
fast. Yeah, otherwise I will cover, but you know that already if you have time, so why do you have to waste your time on next content? You can cover the week four. Up to week four, you can cover.
Okay.
So let me check some questions based on this. If they are, here it is, week six. Let's solve the first graded activity, okay? Not
Yes.
graded, it is
Sir,
activity
one
questions.
point.
Let's see some of them. Yeah, what?
Yeah, actually, I have asked earlier question related to prove the some theorem or sometime some property. We choose a vector like sometime 0 1 0 0 1 1 0 0.
Yeah.
How to choose it? And what is the logic behind it? Actually, can you
It
explain?
basically depends. It basically depends on the situation.
Okay.
Okay. It basically depends what are the cases that we are having. Okay, suppose there was a question. Okay, let me tell you. Suppose I give you any arbitrary order. I want to tell you that suppose one element is given as one, you can take rest of the elements as your choice. So what you can think that suppose if you want to find out the determinant of this matrix, so what you will try to choose more zeros,
Yes.
because finding determinant with respect to the zero row is quite easy.
Easy.
So
Yes.
it depends upon the situation that what do we want. So on basis of that, we take the respective uh, elements. So it depends upon the situation in which we are.
Okay.
We are not even aware that what kind of a thing we are going to take in these cases. So on looking at the situation, we consider the things. Okay.
Okay.
So it depends on the question at which we are working.
Okay. Okay.
So here is the same question, that the same transformation they are giving. Okay. That's fine. Okay. So we have already seen this was the matrix, right? And it is neither 1 1 nor 1 2. We have solved this question just now, if you can remember. Next, let's see. If the matrix corresponding to a linear transformation with respect to standard order basis, okay, both codomain and domain, this is then which of the following appropriate definition of T? Okay, from this, what you have considered, let me take the screenshot here. Okay, so let's crop this part. So this is my question. In this one, it is saying that I am given this matrix. Okay. So I have to find out the general form. What is the general form of the transformation? So as I know from this matrix that if I transform 1 comma 0, so what will I get? Both codomain and domain, we are using the same thing, means 2 times of 1 comma 0 plus 1 times of 0 comma 1, right? And same transformation of 0 comma 1 will be 3 times of 1 comma 0 plus 4 times of 0 comma 1. Okay, so if I want to find out x times of 1 comma 0 plus y times of 0 comma 1 transformation, What is this basically? We have to find out tx comma y. So I can write x comma y as this, right? So if I write this, so this is nothing but x times transformation of 1 comma 0 plus y times transformation of 0 comma 1. Okay. So now what I am saying that transformation of 1 comma 0 is 1 comma 0 is 2 comma 1. So I can say x times 2 comma 1 plus y times 3 comma 4. So if I add these two things, what I get 2x plus 3y comma x plus 4y. Is that clear?
So we could have directly done that using that transformation matrix which is given to 1, 3, 4 multiplied by xy. We could have got the
Yeah,
same.
because it is standard basis, but if some other bases are given, then you have to follow this kind of thing.
Yes, sir.
That's the problem. So that's why I already used the way so that in next of the questions you don't directly get the answer if some basis is changed. So you have to follow this exact method. So that's why I am using this. Otherwise, I would have used that. Okay. So here it is. Anyone having any query, then you can ask directly. Okay. Next is this one. We have solved this, I think. So what did we got? We got this. We got this. What did we get? This one. So it is saying T is what? We have found that it is an isomorphism. Okay.
Click outside.
What will you do? Yeah, matrix representation. So I think I solved. It was
1 by
that, right?
2.
Okay. So now let's continue with those questions that are remaining. So U is given, V is given, W is given, and a linear transformation is given like this. TU is equal to TV is equal to 0, 0, 0. Okay. And TW is this. So what it is saying? Okay. There
Choose
is
the
a
set of correct
transformation.
option.
Okay. Correct option we need to choose. Okay. So one thing, if you are observing here something, that why first option is wrong, can anyone tell me? First option is wrong. Why is it?
TU is equals to TV, which is 0.
Let me tell you why it is. If this is done, let me take a new page. Okay, paint. So let me explain all the options correctly. Okay, cut and okay. So here it is. So why it is wrong? Because if you look here, so what is given here? U is this and V is this. If you look, W is nothing but U minus V. If I am not wrong, is that
Yes, sir.
okay?
Yes, sir, right.
So transformation of W will be transformation of U minus V.
Yes, sir.
It has to
Transformation
be
of
0.
U minus transformation of V. So transformation of U and V both is zero vector. So if I subtract zero vector from zero vector, so what will I get?
0.
But it is not a zero vector, right?
Okay.
So that's why it is wrong.
Yes.
Okay, so that's why it is wrong. So now look at the next option. Okay, TU is given this, TV is given this, and TW is given this. Okay. So what I can see, yeah, the same thing that they are dropping the first column, they are the first component they are dropping. They are using the next two components, right? TU is 1 comma 0, TV is 0 comma 1, and TW is 5 comma 6. So yeah, there can exist a transformation like this. We found the transformation. What are they doing? They are doing this thing. So this is okay. What's the problem in that? Same law is followed here. In when we are transforming U, so they dropped this one and Y comma Z they transform. Means this is transformation of X comma Y comma Z is equal to Y comma Z. This is okay.
But like in the first one, the way we checked this one, right? In the first one, say for example,
Yeah. Yeah.
we can't check anything in the same manner for this one, right?
For this one, Yeah, let's check if these are linearly dependent or not. Okay, if they are linearly dependent, then we can write one as a linear combination of other two. Then we can verify the thing. Okay.
Okay. Okay.
So 2, 1, 0 if I am having, and 1, 0, 1 I am having, and 3, 5, 6 I am having. So if I find out, suppose directly the determinant I want to find out if these are not linearly independent. So
Second column or
let
third
me
column, this is
the
second
third
column.
third row,
Second row or third row.
the third we are, okay, second, let's choose second. Okay. So what will I have? 1, 3, 1, 6 plus 5. Sorry, minus, I think I have to use both sides.
Minus.
Yeah. 2, 1, 0, 1. So if I solve this, so I will get 6 minus 3, 3 it is minus 3, minus
Yes, sir.
5,
Minus
minus 10.
72. Minus 10.
Okay, so it is minus 13 means it is linearly independent. I can't get this
Right,
as a
right.
linear combination of these two.
Okay. 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 Got it.
So this is independent, so I can't use this logic. Okay.
Mhm.
In the next one, uh, we are given three vectors and all are independent, linearly independent, same thing. It is saying
Yes,
that
sir.
transformation of U is zero vector, transformation of V is also zero vector, and transformation of W is also zero vector. Okay, then it is saying transformation of 142 is 241. So this is wrong.
Right, sir. Every transformation is zero then.
I Yeah, because every it is having three independent directions. Okay, and three independent directions are enough to span the complete R3 space. Okay, so there is no point left that I can write with the help of these three vectors. If I write any point as a linear combination of these three vectors, so whatever be my image,
Zero,
okay,
zero,
I
zero.
can write it as a linear combination of these three images. Okay, and these three images are nothing but zero vector. So if I do any linear combination of zero vector, I will get a zero vector. But it is not a zero vector here. So that's why this is wrong, right? Any problem? Anyone having? No? Next is
Okay.
this. Where, yeah. Okay. So in next one, we are having a u vector given as standard basis, same standard basis we are using here, u and v, and we are transforming it as this. So that's fine. Transformation of u 1 comma 0, we transformed it to pi comma 1. That's fine. Okay. What's the problem in this? And same here, transformation of v means 0 comma 1 is 1 comma e. That's also okay. No problem in this because these two are linearly independent, and here we are getting these two linearly independent. They may be dependent, then it is no not an issue, but these are independent, so we can simply conclude with that it is okay.
Sir, here
No
it
problem.
is very logical, means there is no mathematics.
Yeah, there is no mathematics behind this. This is simply just simple logic. Can use. So let's check it, verify it once. This one okay, and this one okay.
I'm really sorry. Would you mind explaining the last one?
Last one.
Yeah,
Okay.
yeah.
First check, sir, it will be fine.
Okay. It is. So this one. In
Right.
u and we have two bases given okay here, so we can
Right.
form any point. Suppose I want to find x comma y transformation, so I will check that whether it is defined or not. So what it will be, x times u and u, so I can write transformation of u plus y times transformation of
V.
v. So what is u's transformation? It is pi comma 1. And what is my v's transformation? It is 1 comma e. So if I add these two values, what I will get? X
And
times pi plus y, okay, as my first element, and x plus
Y.
y times. So that's okay. What's the problem in this? This is linear and that's fine.
Okay.
There can exist any kind of, so there is no problem in that. This is something uh, uh, without any kind of problem. It is okay. There is no problem in this. Okay, let me check this. Okay, here it was. Any question? Okay, all are done right. Yeah, all are done right. Let's move. here. If identity matrix of order 2 is the representation of a linear transformation with respect to the standard basis, both domain and codomain, then it is also a matrix representation of T to any other basis for both domain and codomain. So, okay, what you observed here, they are saying that if transformation is identity matrix, if you form the matrix, so it will be identity matrix like this. Suppose I want to transform 1 comma 0. So let's firstly make the transformation. Okay, so it is identity matrix means this matrix it was. So if I transform 1 comma 0, so they are saying that it will be transformed to 1 comma 0. Okay, or you can write like this 1 times 1 comma 0, and then you can conclude this thing. Okay, this is nothing, same thing. And same 0 comma 1, it is 0 comma 1. So if you want to find out same the T transformation of x comma y, so what you can write down here, you can say that x times transformation of u plus y times transformation of v, same thing. Okay, because it is standard here, so we can write it like this. So what I will get transformation of this is nothing, x comma y I will get, means the point x comma y will be transformed to x comma y. Okay, so in this one, it was saying in the question that if the identity matrix of order 2 is a matrix representation, so it is saying then if we use any other basis, then it is also a matrix representation. Okay, it will be the same thing. So if you use here any other, suppose I want to use any other 1 comma 1 I am using and 1 minus 1. So they both will be transformed to 1 comma 1 and 1 comma minus 1. So it is nothing but 1 times 1 comma 1 and plus 0 times 1 comma minus 1. Here it is nothing but it is same thing, 0 times 1 comma 1 plus 1 times 1 comma minus 1. Because they are transformed to the uh, exact same values that they were and they will be. So the representation of matrix will remain the same. It will be identity for any value you can take, it will be same. Okay, in next one, T be an isomorphism between two vector spaces and A be the matrix representation with respect to some basis, then nullity of A is 0. T is given, okay, T is isomorphism, that's fine, and we are doing some basis, then nullity of A, if it is isomorphism, okay, then of course it is nullity is 0. Isomorphism means it is injective, and injective means its nullity is
It
0.
is zero.
Both are okay. Let's check this once again. So it is saying that if I have a vector space V and I want to transform it to W, so if all of my points here have unique image here, okay, unique image they are having, okay, they don't have same image, so some of the part of this one is covered, so all part of this W is covered, it is saying, means all points inside this are covered by this one, so all points of V is also covered. So if all points of V are covered and W is covered, so where is the null space? So there is no null space left. Okay, so that's fine. So nullity is 0. This is okay. This is okay. And next one is if A is a matrix, this one, okay, with respect to some standard basis for both domain and codomain, then matrix representation of T on T. Okay. If we apply transformation over transformation with respect to the same basis will also be A. It is some kind of a complex question. Let's see. Transformation of standard basis 1 comma 0 is given as, sorry, let me write down the matrix first, 0 0 0 1, right? Yeah, it is. So transformation of 1 comma 0 will be nothing but 0 times 1 comma 0 plus 0 times 0 comma 1. So means it is transformed to 0 comma 0. Okay, next transformation is 0 comma 1. It is nothing but it is going to transform to 0 comma 1. So it is saying if I transform the transformation of any value x comma y. Okay, so what I have to say that, okay, so the matrix representation of this will also be A. Okay, let's see. So if I transform this 0 comma 0, so what will be this? This is nothing but 0 times 1 comma 0 plus 0 times 0 comma 1. So if I do the transformation over this, so it is nothing but it will also be 0 comma 0, right? And if I transform this 0 comma 1, so it will be transformed to again 0 comma 1. So it is having the same, this one, same matrix representation. 0 times here both, and here 0 times and 1 times this. 0 times 1 comma 0 and this one. So this is same. Okay, you can verify this thing. Yeah. What is the difference between these two options? Okay, it is saying identity matrix. No, it is not going to be identity matrix. We have seen so far that it is going to be the same matrix. This, it is not identity. So that's why this option is wrong. Any query? We are writing just, we are applying the transformation twice, nothing else. We did the transformation twice. Okay. We applied the transformation first on a point on this basis. Okay. We got this. We applied the transformation on it. Then we got this value. So we wrote it as a linear combination of this standard basis. Okay. To get this matrix. Okay. Same here. I transformed this value to this and then again took this and do the transformation. I got 0 comma 1 again. So when I am going to write it down as a linear combination of bases, so I can write it as 0 times 1 comma 0 plus 1 times 0 comma 1. The matrix representation I am doing, nothing else. Okay, I hope this is okay. Let's move to the next question. Two questions are remaining, two or three, I think. Beta is given and gamma is given, two bases for R2. If ABCD is a matrix representation of linear transformation with respect to beta for both domain and codomain. Okay. What is the matrix representation of T with respect to gamma for the domain and beta for the codomain? So let's see. Gamma we have to use with respect to the domain. So let's take a new page. Okay, let me print it. That will be okay. So if I paste it here, so let's use beta for the codomain and gamma for the domain. So I can write, how can I write two bases? Okay, it is the matrix representation. Okay, okay, that's fine. Means if I transform 1 comma 1, so I can say that it is A times 1 comma 0 plus B times C times 1 comma minus 1, right? And if I transform 1 comma minus 1, so what will I get? B times 1 comma 0 and D times 0 comma 1. Right, so what do I have to write down? I have to write down the matrix representation of T with respect to this. Okay, that's fine. Okay, that's wrong. I think I have, this is not given. The given thing is this: transformation of 1 comma 0 is equal to A times 1 comma 1 plus C times 1 comma minus 1. Okay, yeah. And transformation of 0 comma 1 is given as B times 1 comma 1 plus D times 1 comma minus 1. So what did I get? A plus C, my first component. Second component is A minus C. Okay, and first component is B plus D. And second component is B minus D. I got from here. So if I have to find out the transformation for use gamma for domain So gamma is 1 comma 1. So I can write transformation of 1 comma 1 as transformation of 1 times 1 comma 0 plus 1 times 0 comma 1, right? So if I apply this, so this is nothing but transformation of 1 comma 0 plus transformation of 0 comma 1. So what is this? It is given here. Next is given here. Okay, so what will I get? If I add these two transformations, so I will get a plus b plus c plus d here. Okay, and here I will get a plus b minus c minus d. Okay, same. If I transform 1 comma minus 1 here, so I can write it as t times 1 times 1 comma 0 plus, sorry, minus 1 times 0 comma 1. So what would that be? It is going to be transformation of 1 comma 0 minus transformation of 0 comma 1. So this will be a plus b minus c minus d, and uh, what is this? A a plus d minus b minus c, right? Yeah, right, I think. Yeah, that's fine. Okay, so I have to write down these things using this. Where is 1 comma 0 and 0 comma 1? So okay, that's fine. So I can say it is a plus b plus c plus d times 0 comma 1 1 comma 0. Okay, and plus a plus b minus c minus d times 0 comma 1, right? Or
So,
something wrong?
sir,
Yeah,
in the second one, sorry, can you go down?
yeah, yeah.
It will be a plus c minus b minus d, right?
A plus c. Why? We are subtracting 0 comma 1. So
Right.
what is 0 comma 1 transformation? It is d minus d. We are subtracting this. Okay, it is okay. Okay.
Sir, why are you applying two times transformation?
What?
Why are you applying two times transformation first with
Okay, okay.
1 0
So
the
I am not
standard
applying.
basis?
What was the thing that I am given this matrix representation when I am using beta for my domain and gamma for my codomain. I am using this. Okay, so now it is saying that use gamma as your domain, basis for domain, and beta for codomain. Now write the matrix. It is saying.
Okay,
Okay,
so
so
first
that's why I
we
am doing it.
okay.
Okay, so that's why I am doing. Okay, that's done. Next is again this thing, but I think I am making some mistake in this one. Let's check.
Sir, you are subtracting this one, right? A plus c from b plus d, right?
A plus C from B plus D. No, I am not. I am subtracting B plus D from A plus C.
Oh,
A
okay.
plus B here minus C minus D. Okay, that's the thing. That's fine. 1 comma 1. That's okay. Okay, that's okay. And when I am using 1 comma 0 here, I got A times this one. Okay, and C times this one. That's fine. A plus C and A minus C I got. B plus D I got. B minus D I got. Okay. So now I am finding the transformation of 1 comma 1 and I wrote it as this.
So this one looks fine, sir. This one looks fine.
This is looking fine.
Yeah, next, the other one is looking a bit.
Yeah, next one, yeah, I'm also thinking that same thing. So if I apply the transformation over here on 1 comma 1, so it is 1 times this, 1 times this. So I should get this. So I am getting this 1 times this one and 1 times this one. When I added these two things, so I got this.
Sir,
Let me
in the
check.
second
Sir,
one, when
you
you
was
in the
What?
second one when you are doing
sir,
the
you are adding
Yeah.
minus c minus d. How you have to add a plus c then b plus d to the 1 0 and
Which one?
0 1.
Where you are saying?
Sir, in the first component where you are adding 1 0, transformation of 1 0 and 0 1, there you are
Yeah.
adding a b plus c d. There we should add, you
A,
should add
B.
a plus c then b plus d. That xx component first, comma y component a minus c and b minus d.
That's also fine. A plus B if I added and C plus D, that's fine. I wrote.
Okay,
These
sir.
two components I have to add. So I added this and this I have added.
Okay, sir. Okay.
Sir, in the
I
next
think
one,
there is some. Yeah.
t10 minus t01, it should be, sir,
Yeah.
a minus b plus c minus d, right?
A plus B minus C minus D. Okay. A plus C
Yeah, exactly. A plus c
minus
minus b
B.
minus d. That was what I was saying.
Yeah, that's right.
And okay, and this one will
Sorry,
be a
A plus
minus
B.
c minus b plus d. Yeah, this is okay. This is okay.
This is okay. Okay, so if I am representing it as matrix, so I am getting something else here still. Let's see. It is not going to be here. It will be here. A plus B minus C minus D. And this will be here. A plus C minus B minus D. And A plus D minus B minus C. So this is my matrix representation, but here something else are given. Maybe
So we
something. I
have
will
to
check that
reduce it.
question.
So do
Let
we have
me
to
check
reduce
this
that?
one. It is saying A. What?
Will we have to reduce that?
Maybe. Uh, yeah, we can reduce it, but no, it is not a good thing to do.
Okay.
Okay, I am getting A plus B is common in all of them. No,
CD
it is
is
not.
every
In fact,
CD is in every column. CD.
CD is okay. Yeah, that's fine, but it is not enough. Okay, if I make the components, okay, if I somehow turn this thing, all are available there in there. Okay, let me check this again. Okay, I will check this question. Okay, then I will come to you. Let's check next question. It is saying that beta is this. Okay, beta is used for both domain and codomain. Sorry, beta is used both. I used gamma here. That's the problem. Okay, I used the gamma here for codomain, but I have to use beta for both of them. So that's why it is having the problem. Let me now explain it again. Okay, the problem was that I was using gamma there. Okay, so let's move. So what I have to do, I have to use this beta for both domain and domain. So it is saying that transformation of 1 comma 0 is nothing but a times 1 comma 0 plus c times 0 comma 1. So it is nothing but a comma c, right? Next is transformation of 0 comma 1. If I use, so it will be b times 1 comma 0 and d times 0 comma 1. So it is nothing but b comma d. Okay, so now it is saying that I have to find out the transformation matrix with respect to the gamma is domain and beta is codomain. So 1 comma 1 if I want to find out, so it is same thing, that transformation of 1 times 1 comma 0 plus 1 times 0 comma 1, right? So if I do the transformation now, so what will I get? 1 times this one, so it is
1 comma
a
0.
comma c I will get. Okay, and here I will get b plus d. So it will be nothing but b comma d, b comma d it is. So I got a plus b comma c
C
plus d.
plus D.
Okay, next is if I do the transformation on this
1
1
and
comma
1.
minus 1. So what will I get? It will be a plus a comma c minus b comma d, right? So it will be a minus b and c minus d, right? So which option it is? First option, I think, this one, right?
Yes, sir.
Earlier, what I was making mistake, I was using gamma. What I was doing, so I was using beta as my domain and gamma as my codomain, but I have to use both. It was written here. Okay, I forgot to see that. Sorry for that thing. Okay, so this option is correct. So now let's move a little bit down. So here it is given. First option is correct, na? Yeah. It is. First is not correct. Yeah. Let's check. C plus D. Okay, okay. It should be transpose. I have to change the row to column. Forgot. I again forgot. C plus D and A minus B, C minus D. Right. This one is correct. This is not. Okay. What we do? We write the row as column, right? When we do the matrix transformation.
Right, sir.
Okay. So
Column.
that's the thing I forgot. Okay. So this is the thing. So that's why it is correct. It is A plus B there and C plus D here and A minus B, C minus D. Yeah, that is.
So we have to write the vector every time in the column form, right?
Yeah, we have to write down it as each row as column.
Okay.
Sir, they do much labor in making question.
What?
They do much labor in making questions.
Yeah. Next is a matrix representation of T with respect to gamma, both domain and codomain. Now we have to use both. Okay. Gamma is domain and codomain. Now let's go here and use gamma. So nothing. That's also okay. Transformation of 1 comma 1 I can write. I have already derived. What was that? 1 comma 1 is A plus B comma C plus D, right? And transformation of 1 comma minus 1, it was A minus B and C minus D. So I have to write down these two vectors as a linear combination of these two vectors. So suppose I write down A times, so not A times, A is already there. So write X times, suppose 1 comma 1 plus Y times, it is 1 comma minus 1. So what I can say, X plus Y is equal to A plus B, and X minus Y, it is equal to C plus D from this equation. So I got 2X value as A plus B plus C plus D, and X value is nothing but A plus B plus C plus D divided by 2. If I put this value anywhere in this equation, suppose I am putting this value, let's subtract. Okay, that will be easy. So 2Y value I will get as A plus B minus C minus D, and if I divide it by 2, this. So I got these two options. Okay, so it will be my first. It is going to be the matrix representation. First column will be A plus B plus C plus D by 2, and the element below it will be A plus B minus C minus D by 2. Its transformation is still remaining, so I will write it as second column, but let's check it is in the option or not. Otherwise, we don't have to do much effort in this if it is already available. So by 2 are there, two matrices are there, okay? And out of them, I have to search for A plus B minus C minus D. A plus B minus C minus D by 2, A plus B, okay, this one is correct. Right? It is matching. Our first column is matching with this one. So that's why it is okay. I don't want to do, you can do by yourself the remaining part. Okay, is that okay? Or should I explain? Okay, I think it is okay. You can see here, A plus B minus C minus D. Yeah, it is matching. Just one final question here. Let's see this. So which of the following options are correct? So we are given some transformation R to R2, okay, is a linear transformation which is both 1, 1 and onto, then T inverse is also a transformation. Okay, if it is both 1, 1 and onto, then T inverse is defined. If I have a transformation from this vector space V to W, I am transforming, okay. So if my all of my elements, it is of R2 and all my elements are getting a unique image every time, okay. So I can say that for every unique image, there is a unique pre-image. It is already given that it is injective. So it is having a unique pre-image. So I can say that T inverse that I am having is nothing but the just inverse relation. All these points inside this R2 will become the domain, and it will become the range space. So that's why they exist. Just it is asking for existence. It is not telling you that you have to define or something do. So it is asking. So it is possible. That's fine. Next is Rn to Rm, and it is saying that some standard basis for Rn. Okay, so it is asking for the order of the matrix that we will get. So as I said, if my vector in V is of Rn, okay, so n components are there. But when I am going to be inside W, so I have Rm. So the vector that I am having here, M, okay, so it can be written as a linear combination of M independent vectors that I will use for basis. Okay, so M vectors are there, but I will make the transpose of this. So M will be here, M number of rows and N number of columns are there. So M cross N it will be. So the third option is correct, I think. Yeah, this one. Next is this. Consider a vector space V where this is okay. This is set of 2 by 2 upper triangular matrix with usual matrix. Okay, that's the same. Then there exists an isomorphism from R3 to V. So it is okay. R3 you have to take and you have to match it with this V. So what you can do, you can simply think that if you have a three-dimensional vector X, Y, and Z, okay, so you can directly write that its general transformation will be X, Y, and Z. That's okay. You got a relation. Sorry, a transformation, not relation. It is isomorph. Okay, you can see there all the upper triangular matrix will have a pre-image in this one. Okay, and each element will have a unique pre-image. Is that clear?
Sir, but what about onto, sir?
Onto, I am saying that it is considering all upper triangular. It is not considering all 2 by 2s. Okay, if it was considering all 2 by 2, then we have 4 independent variables. But now it is considering upper triangular, so this value is 0. It is fixed. Okay, so now it has 3 dimensions. 3 dimension. Its dimension is 3. Okay, so now we have 3 independent variables here. So it is onto. Means suppose any upper triangular matrix you take, any take. Suppose I took 1, 3, 1. Okay, so its pre-image will be 1, comma 3, comma 1. Right? If I take any other, so it will have a all the points in this upper triangular matrix will have a pre-image. Okay, so that's why it is onto.
So does it
And I
need to
said
be
that
an upper? Um,
if it is lower triangular, then also it will work.
so in case it's not neither, and only one of the places have zero, that is on the first place.
Then it is also okay. This is also okay, but make sure that the vector space that is given, that transformation is with respect to V to W. So this W should have only 3 free variables. If this is of a dimension 3, then it should have 3 free variables only. Okay,
Okay.
not more than 3. Okay, otherwise it will not be on 2 if it has 4 or more than 4, more than 3. Okay.
But sir, in this one, in this matrix, so we have only y as the free variable, right? Here.
Here in this matrix,
Yeah.
no, if you are considering it as free variable, I am considering it as here, like, suppose I want the free variables case is not here because we are not using the matrix representation here. Okay, so it is something else that I am conveying here using the free variable term. It
Okay,
means
variable.
that independently they can take value any value.
Okay.
Okay, their value cannot be defined by one another.
Yeah.
They are independent of one another. Okay, so what I am conveying here is this, that you have any vector in this form, sorry, any matrix in this form, so you have a pre-image here, a unique pre-image for
Okay.
all upper triangular matrix, upper triangular matrix. Okay, you
Okay.
have an image is there. Okay, and it is unique.
Okay.
Okay, no two can have same image. You can check this thing that suppose if I give you transformation of x comma y comma z is equal to uh, zero matrix. So 0 0 0 0. So what is transformation of this? It is x y z 0 is equal to 0 0 0 0. If you compare all these equations, so x value you got 0, y
Yeah.
value you got 0, z value you got 0, and 0 is equal to 0. Okay. So all components become 0. Only it is possible when all x, y, and z are 0. So its nullity is 0,
Okay.
right? No null space is there. Null space is having only this 0 vector. So that's why it is injective. And surjectivity, I already told that any matrix, any upper triangular matrix you are taking, so you can write it as a transformation of a vector. So this was the case. Okay. So I think that's enough for today. If any query you are having, then you can ask. Otherwise, I'm going to end this session now.
Sir, in this question, it is given that we are using that upper triangular matrix. Sir, if that
Yeah.
was not the case, then onto would have, I mean, there would, okay, one to one would have not been possible in that case. X, Y,
If
Z,
it is not
because
okay,
only we
if
are
you are
having
saying that,
R3 to R4.
yeah, if R4 it was, then you can say that, yeah, if you are matching it with this four variables you are using, okay, right?
Okay, it would
So you
have been
require a
onto,
four
sir.
variable here,
Yes,
X, Y, Z, and W. Now it will
no, no.
also injective.
Okay, in this, okay, in this example, it is injective and both onto. It can be both injective and onto, but if it would have been XYZ, then onto would have been hampered.
Okay, now you are saying that if it is some variable, yeah, now it will be
So
because
it
it
won't be
can take now
onto.
it is R, yeah, it is a matrix of 2 by 2 now. The
Hmm.
codomain is okay. So upper triangular, let's see, okay, X, Y, Z are there, and this is 0. So we have only images for those matrices which are upper triangular. We don't have
Correct,
other
correct.
matrices, okay, free images. So that's why it is not onto, it is into. It will be into, not
Okay,
onto.
right.
Okay.
On
Anyone
to
else
and
having any?
1 sir, into means
Into is
Into is just opposite of onto.
it's 1 1.
Means not onto means it is into.
Okay, sir.
Okay.
okay.
Onto means the range space is lying onto the codomain space. Okay. Into means this range space is lying inside this codomain.
Okay, sir.
Inside means some
It
of the
will not be
elements are without.
it will
It
not
does
be
not
one.
imply it's 1 1.
It will not one on. It will not be 1 1 also, right?
It will
We are
not
not
also
talking
be
about
one.
1-1.
Yeah,
We
yeah.
are
It
just
may be, but it's not sure.
It is 1 1. Every
One
element
one.
T x y comma z will have one unique element here.
Yeah. Okay.
Here
Okay.
no,
Means
sir, but if into, then we cannot say it's 1 1.
yeah, in two cases, yeah, we can't say that it is 1 1 or not. 1 1 and many one is another case. 1 1 and many one
Right. Right.
is something else, and into and onto are something else. These two are different terms. 1 1 means this injectivity that we said that null space is 0. Okay. And into and onto means range space, sorry, onto means range space is equal to the codomain space. Right? So these two are different properties. If it is not 1 1, then you can say it is many one. And here, if it is not onto, you can say it is into. Okay. Next, the term that they use in most of the books, same is monomorphism. Monomorphism means same injectivity or 1 1. Okay. And epimorphism is this surjectivity or onto. Bijectivity means both 1 1 and onto. So these are term you can read it. Okay. There are a lot of names for same thing they given.
Sir.
Okay. So don't get confused with these terms. Okay. Let me explain it. 1 1, it is written anywhere 1 1. Let me clean this page. Okay. That's enough. 1 1, injective, monomorphism, all are same term. Okay, same thing. Then there is if it is not one one, not one one means it is many one. Okay, many one or not injective. You can say injective or monomorphism, not monomorphism. Okay, this is next is onto if it is written, surjective it is written, or epimorphism it is written. This is same. These are same thing. Okay, so if onto it is not onto, then it is into, or you can say not surjective. Okay, or not epimorphism. Okay, if both one one and this onto, then you can say it is bijective. Okay, or isomorphism. I hope these terms are clear now.
Yes, sir. No clear.
Okay, you can check this. That's it. Any other doubt? Anyone having?
So into is not surjective. Okay, okay, fine.
Just let me close the session. It is live stream. So I hope